Yeah. Okay, so let's do this here. All right, so okay, so the last thing we did was business. Right. I think we didn't kind of improve our way through this yet, so. We talked about it previous past time. Suppose I field K and X an indeterminate. Let V be a valuation domain between K and KX. So V is any valuation domain that happens to live between K and rational functions, in K. And I want to not be whole quotient field as well. So V is evaluation domain, and the conditions are I don't want it to be the whole quotient field KX, but I do want it to be big enough so the ring of fraction of X is in fact K round bracket X. Then V so V takes on one of the following two forms. It is either K of X localized at some F, where F or V is actually K adjoined with X inverse localized at the prime ideal X inverse. Notice that in Kn, this is symmetric to Kx, right? That is to say, you might consider this Ky localized to the ideal generated by y, right? So that's kind of interesting. So if V is a domain between K and Kx, where its quotient field is K round bracket X, then it has to take on one of these two forms. It is either the polynomial ring localized at some polynomial F, or it's K of X localized at K of X inverse localized at X inverse. So let's do a proof of this. Either X or X inverse must lie to B. Right? Because we're assuming that B is a valuation domain with quotient field KX. So one of those two has to lie inside B. If Well, notice that of course, K is contained in V because it's between K and, K round bracket X. And now we know that X is in V, so KX is in V. So V is an overing of a PID and the case PID, V is an overing of it. And so remember, we actually did a problem, didn't we? That every overing PID is a localization. So V is KX localized to F, and F because remember, when you localize, right, your localization of this actually must be an overing of PID, and this PID, and so it's only got, its localization only has one maximal ideal, namely whatever the appropriate F is. So we've got that part flipped. On the other hand, if we have X is not in V, then X inverse is in V. And in fact, X inverse is strictly in V, or KX inverse. This is now a strict containment. And so again, of course, KX inverse is also a PID. So again, we must have that V is KX inverse of localized to some prime P. KX inverse of it. So that's prime ideal. Since X is not in V, then X inverse must be in this prime V. Right? Because if not, then it becomes a unit in here. And so since KX inverse is a PID and the prime X inverse is in that prime, then that must be the prime generator. So there you go. Okay. Any questions? That problem that I gave you for homework, talking about the Prufer domains, one of the many applications of the UU inverse lemma might be that if you decide to do it this way. Use famous UU inverse lemma. This one's like a really, I really dig this lemma. It's very utilitarian. course, you have to have a quasi-local ring, but, you know, that's kind of okay. Theorem. It is actually typically called here humans like now. But we're promoting it, we're giving them field promoting the theorem because it is pretty powerful. But R be quasi-local, image enclosed. Quasi-local, integrally closed domain. With quotes like that. And let U be K. This kind of generalizes the notion of integrality very nicely. If U is the root of a polynomial equation over R with at least one of the coefficients in a unit, then U or U inverse is known R. Yeah, U is root a polynomial equations over R. Yeah, at least one coefficient of unit R, then either U or U inverse. Right. So let me point out that the assumption of this problem is that one of the assumptions is that R is integrally closed, right? And the easiest polynomial equation I can think of for U is a monic polynomial, right? And of course, since it's integrally closed, that means U has to be in there, so good for this. This is a really cool theorem because it says if it doesn't matter if it's not monic, as long as somewhere along the line there is a unit coefficient, that means U is in there or U inverse, perhaps. One of those two has to be. This is really cool. I really dig this. So let's go through the proof. Proof's kind of fun. So suppose that we have suppose our polynomial equation takes on this form, almost right the first couple of terms here. Where of course A and B are in R. The first observation I'm going to make is note. Let's note first that AU is integral over R. Right. So AUN is the leading term. AU actually has the integral on R. Is that completely elusive? Maybe not, right? Let me shore up this statement. Suppose that suppose we write this out a little more explicitly. where all my, relevant, all my players here, all the A and all the B's are in there. Here's what I'm gonna do. Multiply the sketch bang by A(n) minus 1. And so now I have A(n) U(n) plus B(n) minus 1, A(n) minus 1 U(n) minus 1 plus B(n) minus 2, A(n) minus 1 U(n) minus 2 plus B1 A(n) minus 1 U plus B0 A(n) minus 0. And now all you have to do is just kind of collect the appropriate power of A. Notice it's AU to the N plus B(n) minus 1 AU to the N minus 1 plus B(n) minus 2 AN U, or that's not bad. A minus 2 1 minus 2 good. B1 AN minus 2 AU B0 AN minus 1. And notice that AU is in R, but R is in place. Right. And so it's the statement that AU has to already be in R. Okay. If AU is in a unit R, then U inverse must be in R. Okay, so we're done in that case. So we can assume that AU is not a unit. So now let's suppose that AU is not a unit in R. And so let's look at this rewrite equation. I'm in the problem. No, yes, rewrite polynomial equation. This way. I want to mimic what I did over here. So now I've got a smaller degree polynomial here. Remember, AU is in R and B n plus 1 is in R. So now I've got like a sort of smaller equation. If B is a unit, so if we look at this, so if B is a unit, then AU plus B How come? Well, at least can you try for a quasi answer? Well, if B is a unit, and what do we know about a unit? It's not a unit, right? But this ring is quasi-local. So remember, this is a quasi-local ring, so the Jacobson radical of this ring is just that single maximum ideal, and so everything out of that is a unit, right? So this is a unit. If B is a unit, that's a unit, I should say. And U is an integral over R, right? And so it's NR because of the fact that R is enclosed. If B is not a unit, then right? So remember, when we started this problem here, if A is a unit, then because of the fact it's enclosed, U is in there, right? And so we reduced down to this case here, and we found that if Bn plus one is a unit, which I didn't write Bn plus one, but Bn plus one is a unit, then this whole thing is a unit, and we get U as integral, and so in there, right? If this is a unit right here. If it's not a unit, then what you've done is you've lowered the degree of the polynomial down to n plus one, right? And just keep going. But remember, our hypothesis is one of these coefficients along the way is a unit. So at some point, you're going to get a unit coefficient and be done with it, right? So this is really kind of a cool thing. Any questions on that? I'm gonna give you a groovy application. Right. This is one of my favorites, coming sort of from an interest in number theory. And this is like, this is sort of weird number theory, but that's okay. So let R be a Prufer domain with Prufer field K. And let F be any algebraic extension of K and T the interval closure of R and F. So F can be any algebraic extension of K that you want. It can be infinite dimensional. It can be huge. And T, the interval closure of R and F. Then T So rude. So let me give you a couple of, before we prove this, let me give you kind of a couple of applications and places that you can see. What this says, I like to draw a little diagram here. You start with a Prufer domain, quotient field K. And you have an algebraic extension. Doesn't have to be finite. Just anything that's algebraic, no transcendental garbage going on. Then take the integral closure of R inside F. So in other words, you take everything out of F that's a root of a monic polynomial coefficient. All right. This is also proof. And actually, you can prove that F is quotient field T as well. So Prufer builds proof. Here is a number theory. C is a Prufer domain, right? Because if you localize Z at any prime ideal, you get evaluation, right? And in fact, Z is very special. It is in the Noetherian Prufer domain. It's called Dedekind. We've actually done the more general part. We'll talk more about particle Dedekind later. But if you have a finite extension, so this is finite degree. You may remember from 8520 or wherever you may have encountered this, that any finite extension is algebraic, always, right? If you take the ring of integer, or if you take the integral closure of Z in F, this is called the ring of algebraic integers, right? It's where you get things like Gaussian integers and Z joined with square root of -5 and so forth and so on. And in fact, lucky us, this is also a Prufer domain. That's what this theorem will tell us. And in fact, here's something the theorem doesn't tell us yet. We'll get to it later. This is also in the theory. What do you need for that? Well, what you need, the best theorem that I know, what you need is you need this to be the theory and this to be a finite extension. Right? But let me give you another special case. Okay, so you can take the ring of all, or you can take the algebraic closure, Q, right? And you can take the integral closure of C in this. This is called the ring of all algebraic integers. Right? This is a Prufer domain, as a matter of fact, by this theorem, because it is the integral closure of a Prufer domain and the algebraic extensions quotient field, and the algebraic extensions quotient field. This one's actually kind of fun because this one's actually not only Prufer, it's basic. So all the finally generated ideas are not only invertible but principal, right? So this is kind of nice, and actually, hopefully, later in this course, we'll see why it happens to be basic. Prove that later. And of course, there's all kinds of other intermediate proof domains that are very big. For example, you can take this ring, or you can take this field here and intersect it with real numbers, for example, and get a slightly smaller version of that. Still proof. Okay. Any questions? Let's prove this. This is going to be fun. Well, so we've got this situation. So let in integral closure of R and F. So we have R as Prufer, T is integral closure of R in the field F. We want to argue that T is Prufer, so let in or ninth quantile T. We need to show that when we localize T and N, then it's evaluation domain. Then we'll be very happy because T will improve. Right? Very good for that. So strategies, we just want to show that when we localize the ninth quantile, we get evaluation domain. So let M be the intersection of N down below. And we want to show, like I said, the T localized in its evaluation domain. So let lambda be an F. Note that lambda is note that lambda, any lambda in F is the root of some polynomial equation over R. How do I know that? Well, I know it's the root of a polynomial equation over K because lambda has to be algebraic over K. So look at all the coefficients in K and just clear the denominator, right? And so now it's the root of a polynomial equation with coefficients in R, right? But maybe it's not mine, right? Since R localized again is evaluation domain. Oh, actually, I want to go for RN. There we go. And my slip is easy to cover because my previous statement was correct, and that it's certainly everything satisfies the polynomial equation over R, right? And any polynomial equation over R is a polynomial equation over R localized M, right? You just got more freedom for R localized M, so no problem there. So since R localized M is evaluation domain, we can assume the coefficients polynomial. Here's my polynomial that lambda's root of. Okay, so how can I make that call?
That just about in the previous result.
Maybe get back and remember the previous result.
Yeah, it just seems to have a similar setup with one of the coefficients being even.
The important thing, right, is this is evaluation domain. So look at read this polynomial's coefficients, right? Because the fact this is evaluation domain, one of those coefficients has the smallest value, right? So suppose the other is minimal, has the minimal value. This implies then RI divides all the other coefficients, all right? So if lambda a root of n is the root of Rn over Ri, X n plus R I plus one over R I X I plus one plus X I plus R I minus one over R I X I minus one plus R zero over R I. Right, because all it is divide out by constant, Lynn's still rid of that, so there's at least one, if not maybe some others sprayed out in there that have that is root. So no, now. Since the cosmological either span, and there you go. So the n is and so T. So there's one application of UU inverse lemma. Okay. Any questions on that? Okay, so let me get you started kind of on the next. We're going to, now that we've armed ourselves with this, so we've talked about Prufer domains a little bit. And I'm gonna have to dive back into integrality a little bit because I'm gonna do some things about how many of you have ever heard of so we're gonna explore some properties of chains of primes, if you will, in Canadian rings and ring extensions. How many of you have heard of line over? You've probably heard that come out of my mouth. Line over the property of primes. In a little ring, big ring, we say that a prime here is laying over by a big prime here. If this can be realized as the intersection of some prime down here. How many of you have heard of going up, going down, or heard that terminology? Or the ink property, the incomparable property. We're going to explore that aspect of integrality. Let me get you started off with this. So more of a dive into integrality theorem. Let R inside T be rings and U an element of a ring containing. If U is integral over T and T is integral over R, U is integral over R. Yeah, U is integral over and T is integral over R. So U is an integral element over T, T is an integral extension of R, then U is integral over R. Actually, I had somebody just when I gave my talk this week asked me a question that was answered as a consequence of this. This is transitivity of integrality. So if something is integral over this ring and this ring is integral over the small ring, then there's polynomial take all the way down to the smaller ring in one step. So we'll see why this is true next time. Any questions?
What's the section heading title?
More on integrality is what I call it, yeah. Okay, other questions? All right, well, give me a holler if you need me today, otherwise I'll see you guys on Monday. So, Al, don't forget my upload, it'll be good. See y'all.
It's more on integral.